Swayam Prabha. Digital India. Educated India.
Now it's already 12:30. Give me 10 minutes. Let me talk about CH4, methane. So CH4 is a problem that is not very easily handled if you don't use the character table. Okay. Which point group is this? Tetrahedral, TD. So what I'll do is, what is the slide number? I'm a little lost now. What are the symmetry operations? Tell me. E, then how many C3s? 8 C3, very good. Then 6 C2 or 3 C2? Why 6? 3 C2s, right? This and this, and C2 plus C2 minus, they are one and the same. 3 C2. Then I, no I. There would better not be I in a TD point group. If there was an I in TD point group, all your stereochemistry would have gotten messed up, right? The whole premise of stereochemistry is the absence of I in TD point group. Okay. Then what else? Any alternating axis of symmetry? 6S4. Then how many sigma Ds? This is an axis. This is one sigma D, this is one sigma D, right? One pair for this, one pair for this, one pair for this. So 1 plus 1 plus 1 is not 4, it is 6. No? One pair for this axis, one pair for this axis, that is 4, and one pair for this axis also, 6. Right? 6 sigma D. Now what I can do is, I can use as usual, how many hydrogen atoms are there in CH4? 4, right? They are the pendant atoms, carbon is the central atom. So I can construct gamma SALC by using the 1s orbitals of hydrogen atom, right? Character of E will be 4. What will be the character of C3? 1 or 0 or 2? 1, not 2, because don't forget what we are doing. We are constructing symmetry adapted linear combinations of the pendant atoms, right? So we don't consider the central atom. We consider this and this and this and these, the 4 circles. We do not consider the orbitals of carbon. Are we okay? Understand what we are doing? First job is to construct the SALCs of the pendant atoms. Shubhangi? Okay. 4. So C3 is going to be, character is going to be 1. What about C2? C2 has to be 0, right? Because this interchange is going to take place in pairs, no matter which C2 you use, 0. What about S4? Of course 0. Sigma D. Remember how sigma D is? These are 2 bonds. Sigma D is like this, right? Sigma D contains 2 bonds. And the answer is not 3, answer is 2. Because once again we are considering the 2 hydrogen atoms, we are not considering the central carbon atom. We are right now only considering the symmetry adapted linear combinations, nothing else. Are we convinced that it should be 2 and not 3? Very good. 2. 41002 and TD is not even an infinite group. So, we can use our old faithful. But looking at the kind of frown on some of our faces, I will write the answer. Yeah, good thing that you can see your own face. But even before writing that answer, I want to make a point. And this is a point that will perhaps make us understand why we have to do this in the first place. Now, suppose you think of valence bond approach. You have 4 bonds, right? Or suppose you think of localized molecular orbital approach. Localized molecular orbital approach would be first generate the 4 sp3 orbitals, okay, and then combine each of these sp3 orbitals with an atomic orbital of hydrogen. So, you get 4 molecular orbitals which are separate, right? What will the molecular orbitals look like? I will just draw the one for this. So, maybe first generate the sp orbital of this and then combine it with the 1s orbital of hydrogen. This carbon, this is hydrogen. So, you get a molecular orbital that looks like something like this. Okay. How many such molecular orbitals would be there? 4. And would they be all equivalent or no? They should be all equivalent. So, they should be degenerate. And what have we said in one of our early classes, many of our early classes, that degeneracy and symmetry go hand in hand, right? Right or wrong? Degeneracy and symmetry go hand in hand, right? So, these 4 degenerate molecular orbitals should belong to one symmetry species, right? Right or wrong? They should all belong to the same symmetry species. What would be the dimensionality of that symmetry species? 4, right? We have 4 distinct molecular orbitals, and if we take the localized demo approach, then all 4 are equivalent, but they are separate, right? So, they should form a 4-dimensional representation. Now, look at the character table of TD, which you had so nicely worked out in the mid-sem. Show me a 4-dimensional representation here. A1, A2, E, T1, T2. Do you see a 4-dimensional representation? No. What is the maximum dimensionality? 3. So, what we are saying is that it is not possible that localized demo picture where you have 4 equivalent bonds like that, it is not possible, right? 4 MOs, 4 MOs, right, which belong to the some symmetry species is not even possible. Okay. So, localized demo picture fails the symmetry test. As we will see, delocalized MO picture passes the symmetry test, but also accounts for the fact that all 4 bond lengths are the same. Sounds oxymoronic, right? So, all 4 bond lengths have to be the same. It is not as if in methane one bond length is more, 3 other bond lengths are different or something, right? All 4 are the same. You have to explain that. At the same time, you have to account for the fact that you cannot have 4 molecular orbitals which are degenerate. Okay. This is what your localized molecular orbital cannot do, and as we will see now, delocalized molecular orbital theory can actually do it. So, let us get back there. So, once again, so what am I doing? I am having too much of degeneracy in my slide numbers. Earlier one was 8, this one is also 8. This is not degeneracy, it is redundancy. What was I about to do? I was about to pay respect to the frowns and write the answer. Break this down. What you get is, you get A1 plus T2. Four SALCs, one is A1 and the remaining 3 jointly form the basis for T2. You can work it out. You can work it out using that example, that relationship, 1 by H sum over R chi IR, and the answer you will get is gamma SALC is A1 plus T2. Okay. So now we have to worry about what is A1 combination and what is T2 combination. A1 combination is very simple, isn't it? Achha. We learned to draw this tetrahedron inside a cube. Let me do that. What I will do is I will draw a solid circle for plus and a hollow circle for minus. So, will you agree with me that this would be an A1 representation, totally symmetric representation. This will be the basis for a totally symmetric representation, right? What will it be then? That SALC, I will call it phi 1. Can you read? Zoom out a little bit. Phi 1 is 1 is A plus 1 is B plus 1 is C plus 1 is D. 1 is usual meaning, A, B, C, D, let us say, are the names of the atoms, identifiers for the atoms. Alright. What will be the normalization constant if I want this to be normalized? Half or 1 by root 2 or 1 by 4? Okay, we have agreement up to here. Should I put the root sign or no? No root sign. Right? If you try to normalize, what will you get? Cross terms will all cancel. So, you are left with whatever is there outside, right? So, this square, if this is C, you are going to get C square multiplied by 1, C square multiplied by 1 plus 1 plus 1 plus 1. Isn't it? Because 1SA, 1SB, 1SC, 1SD are all normalized to 1. Okay, and they are orthonormal set, right? So, multiply them together. Let us say this is C. You are going to get C square multiplied by 1SA square plus C square multiplied by 1SB square plus C square multiplied by 1SC square plus C square multiplied by 1SD square. Now, all these are 1, right? So, you get 4C square equal to 1. So, C square is 1/4, C is half. Okay. You will get 1 by root 2 when you combine two wave functions, right? Fine. So, phi 1 equal to half and everything is plus. That is fairly easy. How do I construct the other one? How do I construct the T2 set? I can think like this, it is triply degenerate, right? Which symmetry operation is triply degenerate? C2, we have 3 C2s, right? So, they should be kind of symmetric with respect to C2. So, I can draw like this, these two can be plus and these two can be minus. Because this is symmetric with respect to this C2, isn't it? There are 3 C2s and we are talking about a triply degenerate set here. So, let us see, let us try combinations that are symmetric with respect to the C2s. So, if I have 2 plus and 2 minus kind of combination, they will be symmetric with respect to C2. Okay. So, I write those 2 plus and 2 minus combination, phi 1, phi 2 is equal to half 1 is A plus 1 is B plus minus 1 is C minus 1 is D, phi 3 equal to half 1 is A minus 1 is B plus 1 is C minus 1 is D, phi 4 is equal to half 1 is A, then what should it be? all right. So, these are the SALCs that we have generated. First one is A1, the 5 2, 5 3, 5 4 jointly belong to T2. Let us see if that is correct or not. Huh? Remember what 5 2, 5 3 and 5 4 look like, right? 2 plus and 2 minus. Yes, sir.
These are in the increasing order of nodes.
No increasing order of nodes. They are same order of nodes. All look like this. You just turn the cube around. See, this is not a linear molecule. No, it's a tetrahedral molecule. Don't forget that. All I am doing is in a tetrahedral molecule, I am saying that 2 are plus and 2 are minus. Now, if I say this is plus and these two are minus, it remains the same. Number of nodes doesn't change, right? You are only turning. You are turning the whole box. Okay? Why? I think like this. Oops. Huh. But then A, B, C, D are degenerate, they are same, don't forget, all are hydrogen atoms. You will get the same thing back. See, all you have to do is set this to be plus, okay? 3 atoms are left, move the plus sign from here to here to here, you got your 4. Now, whether you start with this or you start with this or this doesn't really matter, all are hydrogen atoms, isn't it? Yeah, you start from here, no problem. But eventually, it is 2 plus and 2 minus. That's all that matters. Now, who has said that this is A and this is not A? Okay, so you cannot give too much of importance to the starting point. Once you fix the starting point, then the others become important. Right? Okay. Let us see. Let us have a look at the character table then. Or shall we just work out the, why have I written there? It's sad. What will be the characters of these combinations? I'll do it on a separate page. We are talking about something like this. Right? These 4. And then you just turn everything around. This is a set, right? Now, what will be the gamma for this? Character for E will be 3, character for C3? What will be character for C3? It's a little difficult, right? You have to look at the, you cannot do it just by this. You have to actually look at, you have to look at this and see how signs change and all, you can work it out. Anyway, it belongs to T2. Work it out if you want. It's a little too problematic. Fine. So now what do we have? We have 2 kinds of SALCs. One is totally symmetric, the other is triply degenerate. Now, if you look at this, will you agree with me that symmetries of these match the symmetries of the p orbitals? Let me draw p orbital. Now this is the center of the box, right? You have to pardon my bad artistic skills. This is what a p orbital on carbon will look like. So now see, matching. Okay, and if you don't believe my diagram, you should believe the character table. Can you read? No. Now is it okay? Where do X and Y and Z belong? T2, right? X, Y and Z jointly form the basis for T2. So will Px, Py and Pz also not jointly form the basis for T2, right? So see, we have matching symmetry. The 2s orbital of carbon is in the same symmetry species as the symmetry combination A1, okay, and this T2 SALC also finds a match in the Px, Py and Pz orbitals. So this is what we should combine, A1 with A1, T2 with T2, alright. So we have two kinds of orbitals then. Let me just show you. So these are the combinations that you get. Alright, this is the diagram that I wanted to draw but failed. Right? No, it did not fail. It's just that this is a little better because it's printed. Here you see this is the first SALC that we generated, right? Okay, this is how it is, and you can see that it matches the symmetry of 2s. These are the other SALCs, okay, right or wrong? Now if I want to generate the molecular orbitals, what will I do? These are the molecular orbitals that you get by combinations of A1 atom, A1 atomic orbital for the central atom and the A1 SALC. Phi 1, what was phi 1? Remember? Capital phi 1? This was capital phi 1. Right? All plus. So what I am doing essentially is I am combining the 2s orbital of carbon, which is also A1, with the A1 orbital, with the A1 SALC that I get from the pendant atoms. In one case it is plus, in another case it is minus. I do not know what is C1 and C2. C1 and C2 remain to be determined. Okay, and that is something that I cannot determine from simple symmetry arguments. That is where your computational chemistry CH4 to 5 comes in. CH4 to 5 is not computational chemistry, but chemical bonding nevertheless. CH4 to 5, CH504. 504 is definitely a computational chemistry course. That is where they come in for determination of the coefficients. But this is the kind of combination that I need, right? So already constructed two MOs. Then what are the other combinations? This you agree that I have to combine the other three SALCs with the p orbitals, right? You do that, this is what you get. Moreover, what I do is I know which one matches the symmetry of px, which one matches the symmetry of py, which one matches the symmetry of pz. Understood or not? See, take this example, A is plus, B is plus, C and D are minus. The way that I have drawn it, that has matching symmetry with this pz orbital only, not with px or not with py. So there is no point why there is no point in combining px and py with this SALC, right? I will only combine it with z, right? Similarly, let us say this is x direction. Then the second SALC where A and D are plus and B and C are minus, that would have the same, would have compatible symmetry with your Px only. There is no point in invoking Py and Pz for that. So see, what symmetry is helping us do is that it is helping us decrease the number of terms in every linear combination. If you try to perform a linear combination of atomic orbitals without any symmetry consideration, then you have to combine everything with everything, right? You get a huge number of terms. So essentially symmetry helps us simplify the problem by restricting the number of terms in every linear combination. Understood? So this then are the other molecular orbitals. They are all sigma orbitals, right? C5 2pz plus C6 phi 2 and so on and so forth. When you do that, now I will show you the energy level diagram. See what happens. You are all familiar with energy level diagrams, right? The energy level diagrams you have been drawing from, I don't know, class 12 maybe. So this is a situation, this is a central atom, carbon, 2s of A1 symmetry and 2px, 2py, 2pz of T2 symmetry, and we have generated the SALCs from 1s and we broke them down into A1 plus T2. So A1 set will combine with A1 set, you get 1 here and this is the anti-bonding one, and then T2 set combines with T2 set, you get a triply degenerate level here and you get a triply degenerate anti-bonding level here. Okay. Before I start filling in the electrons, is there a question? There should be at least one valid question here. No question? Which one? Because we generated that way, right? When we generated the SALCs, we saw that one is A1, the other is T2. So whenever it is T2, that means they are jointly forming the basis for the T2 symmetry. And when they jointly form the basis of some symmetry species, we have said that they have to be degenerate. Oh no, this is schematic. This is schematic. Don't worry about that. In any case, these are the energies that are more important. That is the question I was looking for. The honest answer is we cannot really draw quantitatively here. This is only a qualitative picture. You know, looking at number of nodes, okay. But if you really want to put numbers here, then you have to go all the way and do the computation, okay. This is only the expected scheme, looking at the symmetry and number of nodes and all that, fine. So now what is it that we have got? We fill in the, how many electrons will be there? How many electrons? 4 from hydrogen. How many from carbon? 4 from carbon. The n equal to 2 electrons. Right. So 8 in all, 1, 2, 3, 4, 5, 6, 7, 8. Alright. What is total sigma bond order? 8 electrons, all in bonding MOs. So bond order is 8. Is there any other combination? No, but line of thinking is right. It is 4, 8 by 2, right? What is the definition of bond order? Number of bonding electron pairs, you can put it that way, okay. Number of bonding electron pairs is 4 bonds, but you see one bonding pair has a different energy compared to the other 3. So that is where we become compatible with the symmetry argument. We do not have 4 degenerate orbitals. Alright. But then the question that comes now is, does this mean that one carbon hydrogen bond is different from the other 3? No. Why not? Because don't forget what we are doing. Here we are talking about delocalized molecular orbitals. All molecular orbitals are actually delocalized over all the 5 atoms. Right? What does this look like, this A2? What would it look like? Remember? This is what it would look like. Huh? So A1 is spread over A, B, C, D and carbon. It is there everywhere. It is not one of the bonds. It is not CA bond or it is not CB bond. All we are saying is that it contributes equally to all the 4 bonds. That is what is important to understand. Are you okay with this? You understand what we are saying? This molecular orbital here contributes equally to all the 4 CH bonds. It is delocalized. Similarly, each of these bonds that we get, each of these bonds are also completely delocalized over all atoms are involved, isn't it? Right? So, each of these molecular orbitals contributes equally to all the 4 CH bonds. So, eventually the electron density between carbon and any given hydrogen atom is the same. Okay. So, this is something important, this is something that we sometimes miss when we talk about molecular orbital description. Please understand this, a molecular orbital is not a bond. Okay. A molecular orbital is not a bond. Molecular orbital is actually distributed over the entire molecule, right? So, every molecular orbital effectively contributes to every bond that is there. By bond I mean individual bonds in the VB picture, right? So, that is why, so if it is best to think in terms of electron density. Contribution of each molecular orbital to the electron density between any 2 atoms, carbon atom and any hydrogen atom is the same. Okay. That is why all the 4 CH bonds are equivalent. This is not a bond, these are not bonds, these are molecular orbitals. Is that point taken? Now, so next, once again what we had, what Max Planck had said was experimental results are the only truth, everything else is poetry and imagination. So, I had better show you some experimental result if I am to tell you that this is the right picture and not your valence bond picture, not the localized demo picture, and that comes in the form of, almost done, 2 minutes, that comes in the form of photoelectron spectroscopy. What is photoelectron spectroscopy? What you do essentially is that you shine the molecule with light, and you shine it with light which has sufficient energy to ionize the molecule. Alright. So, you ionize it and the electron is then liberated, right, liberated from the it becomes a free electron. Once it becomes free electron, it will have some kinetic energy, right. So, this is the relationship. So, actually I should write H nu equal to IE plus KE. The total energy supplied first of all ionizes the electron, takes it to a level where it just about loses the attraction, and then some residual kinetic energy is imparted to it. So, it is like the first stage of sending this Mangalyaan out of the Earth's orbit. Now, you give it sufficient energy so that it loses its attraction for Earth, and then you give it a little more, it gets some kinetic energy. What, she was involved in it? And why is she being congratulated for it? Alright. Alright. Terminal velocity is different. This is escape velocity. Alright. Okay. So, this is what you do, and then you plot the intensity versus ionization energy. Ionization energy, what is the meaning of ionization energy? Let us take these MOs for example. If I completely ionize this, the energy required to ionize it would give us the difference between, say, that infinite level and this, right. So, which would have more ionization energy, this or this? This would be more, right, and these 3 molecular orbitals would have less ionization energy. Now, if you look at the photoelectron spectrum, this is intensity versus ionization energy. What do you get? Look at this intensity, actually area under the curve, and look at this area under the curve. This is approximately 3 times this. Okay. Is this lower or this is higher? Lower. This is like maybe 12 electron volts, and this is more like maybe 22 electron volts or something. This 22 electron volt band is 3 times less intense compared to the 15 electron volt band. Is it not consistent with the qualitative picture that we had developed? One bonding MO is lower in energy, and then we have a triply degenerate bonding level, triply degenerate MOs are there. So, this is the experimental results. So, whatever I had drawn there, that gains some support from here, right. And if you are an experimentalist, now you can kind of thumb your nose to the theoreticians at this point of time, because what you can do is you can simply now write the energies from the experimental values, okay, and then tell the theoreticians, get me these energies if you can, okay. That is what happens very often, okay. To conclude, what we see is this picture that we develop of delocalized demos using symmetry seems to be giving us some correct result. Just one point, you see this structure here, what does that stand for? That is basically vibronic structure. There is a bound state, isn't it? Bonding means is a bound state, it is going to vibrate. So, when it vibrates, you get this vibrational structure, because the potential energy well will be something like this. You can have this transition also, well actually from here to up somewhere here. So, vibrational structure is a marker of bonding molecular orbitals. We will come back to this maybe in the next class. Okay. So, we see that molecular orbital, delocalized molecular orbital is the way to go, and symmetry helps. But I think you have realized by now that one difficulty we have is, see, BH2, even CH4 are okay, but how much time did it take us? We have overshot by 35 minutes today. How much time did it take us to do this treatment if you have to actually look at character tables, look at orbitals and do it? You cannot do it for really big molecules. So, for that, once again we want to develop a machine that will do the dirty work, difficult work for us, and that machine of course is provided once again from the power of great orthogonality theorem. So, next day actually I was planning to discuss carbon dioxide, but maybe we can come back to it later on. Next day let us do this, let us discuss something called projection operator. We will derive the expression for projection operator, and you will see this projection operator is like a magic machine that takes in some arbitrary function and spits out linear combinations. After all, what we are trying to do is we are trying to develop symmetry adapted linear combinations. So, this machine that we develop, the projection operator, will do that for us. All we have to do it, we have to mechanically use character tables, but before that we had better derive it. So, we will derive what is called the complete projection operator, then we will see that that also is too much of hassle. So, we will derive what is called the incomplete projection operator, and that is what is going to help us throughout the remaining lectures that are there in this course.